now for our second presentation, Short Infeeds Big Results, a guide to short coupled edger performance. We invite Joey Nelson, president of JoeScan, and Peter DeLue, a consultant at Yield Strategies, to the virtual stage. They will be discussing strategies and practical approaches to maximize throughput and recovery for lineal edgers with short infeeds. So take it away, Joey and Peter.
Thank you, Ellen, and thank you, Canadian Forest Industries. So our talk is going to be on kind of a unique edger machine that we think is a really interesting option that a lot of mills could take advantage of, which is a short coupled infeed edger. So I'm Joey Nelson, and I started JoeScan in 1999 to make scanning simpler and more reliable. The first systems we did, many of them were lineal edgers, and lineal edgers really were a way to make the edger machine simpler and more reliable, fit very well with our scanners. The one difficulty is that they often didn't fit in a sawmill. So with the advances of technology in scanning and in higher processing power in computers and improvements in controls, there's now really the opportunity to get that same kind of simplicity and better mechanical system that a lineal edger gives you in a much shorter footprint. And I'm really excited to have joining with me Peter DeLue, who's one of the pioneers in the short infeed technology. And I'll let him kind of take the beginning of this presentation talking about the whole system of short coupled lineal edgers. So.
Good morning, everyone. My name's Peter DeLue. I have a consulting business today working with sawmills on efficiency. Prior to 2006, I was a partner in Innovec Incorporated, which is now part of USNR. And during that time, I was the R&D manager and took care of all of the new developments we did. And 20 years ago, we saw the need for an optimizing edger that could replace manual edgers that simply didn't afford enough room for traditional edger footprints, and also often fed from both sides. So we saw this type of lineal edger with an extra short infeed as a way to fill that need, and we developed a product for that. I'm very fond of this type of edgers. I work with a lot of edgers in the mills who are my clients, trying to keep things in tip-top shape. We're always testing those edgers and watching for what's wrong. And the short coupled lineals are pretty easy to take care of. So short coupled edgers, lineal edgers, fit a particular niche in the mill. They work well where you have a small footprint. They come with a little baggage that there's a limited amount of throughput and the pieces need to be presented weighing up. And developing controls for this product was a challenge because you have to do your scanning and optimizing in a very short period of time because there's a short distance from when the scan begins to when the piece enters the saws. So with a short coupled lineal edger, you can fit into a different footprint than you do with either of the more traditional styles of edger, the transverse or the long lineal edger. Transverse edgers require quite a bit of sideways movement so that you can do the scanning before you make the 90-degree turn and go lineal. And lineal edgers require quite a bit of lineal space after you load a piece onto the belt. So a little bit of sideways movement, a lot of lengthwise movement. And the short coupled lineal shortens up that lengthwise movement as much as possible and gives you some of the advantages of both. So when we're looking to replace an edger, we're looking at increasing throughput, improving recovery, and going for less maintenance. And sometimes a requirement is to optimize an edger, where you're going from a manual edger. You can see here in this picture what a short coupled lineal edger looks like. You're loading onto a rubber belt, and then you transition through a very short scanning zone. You move onto a roll-fed edger box that swivels like a traditional lineal, and the saws move sideways. So the piece never stops moving straight forward. You don't have to skew it like you do on a transverse edger. The saw box and the saws do the skewing. I am losing my control for advancing the screen. Joey, do you have that on your screen? Can you do it for me? So short coupled edgers have these two limitations. You can only go so fast with it, and you need to present all the pieces weighing up. So there has to be a way to be turning those pieces weighing up. If you can work within those limitations, it's a really nice kind of package. In terms of the limitations on throughput, there's no absolute line on that. It would be 12 to 20 pieces a minute, depending on a bunch of factors like your average length and your sawing speed. But you can have a short coupled linear that's not quite as short coupled as a normal one. If you have a little more run room as you approach the saw, then the piece count can go up. So there's kind of a hazy middle ground there between a short coupled and a long coupled lineal. Really the defining feature of a short coupled is the scanning, in that you use a scanner that allows you to scan in a very short amount of movement on the belt. Next slide. Oh, I've got it back here. As I mentioned earlier, why do we replace edgers? We're looking for throughput, recovery, and something that's easy to set up and maintain. The old edgers just requiring too much attention. That kind of boils down to these four factors: throughput, simplicity, maintainability, and accuracy. Short coupled lineals have significant advantages in these departments in terms of simplicity, maintainability, and accuracy. But they have limitations in terms of throughput. So in terms of throughput, the main thing is you don't want to create a bottleneck. So your mill either matches the limitations of this sort of edger or it doesn't, and you want to be careful about that. The thing to do is measure what kind of piece rate it takes to not have whatever your surge capacity is overwhelmed by small surges in production as you go along, so that you don't slow down the mill with the edger. In terms of simplicity, here is a video of a traditional transverse edger and a lineal edger short coupled on the right. The transverse edger has more moving parts, you have quite a bit that has to move to make that 90-degree turn, and a significant amount of that is pneumatic. And as I work on transverse edgers, that tends to be a touchy issue. Things get a little sticky, people turn up the pressure. Now the machine acts differently, the timing is different. You have to keep that tuned up, and you're coordinating movements in a fraction of a second that are quicker than you can actually see, so you have to experiment. Short coupled lineal story is different. It's harder to calibrate than a transverse edger, but it's not hard to calibrate, it's just a little harder. You have a belt to maintain, you've got to keep that running straight instead of feed rolls or a feed chain. And you need to keep it where the piece moves really straight through the edger. That's where your accuracy lies. And when that's not right, if the piece starts to walk a little as it goes through the edger, it can be a bit of a mystery to figure out what's going on and correct it. But the bottom line is short coupled lineals are mechanically simpler and have fewer moving parts. And that translates straight into having a more maintainable machine with fewer wear points. In the short coupled lineal, there's just less that happens that impacts saw line accuracy. So the short coupled lineal has a fairly short list of typical long-term maintenance issues. The belt starts wandering and you have to do something about that, replace the belt or work with the rolls. You get play in the skewing mechanism and you have to take it out again. You get worn machine press rolls and you have to replace them because that can steer the piece off of a straight path. And your typical scanner issues that you would get on any machine with a scanner. Maintaining either type of system, you have to keep the scanner in good shape, but then they're rather different. Transverse edger is all about keeping registration between the scan that you took while moving sideways and the cut that you take while moving lengthwise. And you have to keep registration around that 90-degree turn as you skew and position the piece on the table. And that involves, as I said before, a lot of events that happen in very quick succession that involve pneumatics. So that's the challenge, to keeping it right. Lineal edger, on the other hand, is about aligning things perfectly so a piece travels straight through the machine. If you get that right, the rest is pretty easy. Then you just need to skew accurately. When you ask for the saw box to go to a certain angle, you really get there, which is a matter of calibration. And you need to begin slewing at exactly the right moment. In terms of keeping a short coupled lineal running well, the central thing is doing strip tests, which show you that your saw lines are being laid down the way they're intended. And I'll talk about strip test in a minute. And then watching for gaps in the edge of the piece on your graphics, which would indicate weak scanner performance that needs to be addressed, or sometimes just means the scanner needs cleaning. You need to place the calibration object very carefully when you calibrate. It's a static calibration, and the piece needs to be in exactly the same place every time you calibrate. You need to take care of your belt because it's really part of the scanning system. If that belt is wandering side to side, you scan the piece in one place side to side, but then it ends up being cut in a different place. You need to take care of worn feed rolls and pitch buildup on the rolls that might steer the pieces, and you need to watch for play in the skew mechanism. The accuracy is a marriage of three things. It's scanning accuracy, optimization accuracy, and sawing accuracy. And it bears pointing out that the real performance of a machine in a mill over time is about how well it's performing on its average day, not how well it can perform. So that average performance is about how much things slip before you notice it, and how much you can bring it back to its previous performance. And in the meantime, you're averaging in some performance that's less than optimal. And this is a diagram to kind of point out that short coupled lineals, you probably won't have an issue to deal with as often, and you can bring them back to closer to their original accuracy. The degrading over time that eventually leads you to a sort of total rebuild situation is slower. So advantages that short coupled lineals have in terms of accuracy are there's really good registration between the scan and the cut, because it's a very short movement from the one to the other, and the piece doesn't have to be physically skewed. So if you machine set up well so it doesn't jostle the piece, it shows up almost exactly the way you scanned it. And also compared with transverse edgers, it doesn't have a problem with unstable edges. If you're positioning a piece with a transverse edger that has knife wane on it and the edge is a little bit fibrous, that edge is going to crush as you move the piece into position, and you won't end up positioning it where you expect it to. But a short coupled lineal doesn't depend at all on the integrity of the edges or lack of stringy bark there. It doesn't matter in terms of its accuracy of laying down the saw line. So that's a definite advantage with some kinds of wood. In terms of making sure that it is running as it should, the strip test is sort of essential. And just wanted to mention that the type of verification system that can tail an edger and tell you when you're starting to lose registration between the scan and the cut, that is a great kind of system to put behind this kind of edger, because that is the central test for keeping it running well. So this is a schematic diagram of a strip test. You ask the machine to cut a strip of a specified width from an already sawn board edge, and then place another saw to make a board so you can check the width of the board. So for example, on that left-hand picture, let's say I asked it that the strip would be exactly 25 millimeters wide. I then measured that strip after the cut, and if I find it to be very close to 25 millimeters wide from end to end, then I know the saw line was laid down exactly as it should be. And then I can measure the board and make sure my saw spacing is good as well. The pictures on the right show you things that might happen when your accuracy of laying down saw lines is not right, and then you have a problem to address, and the exact nature of how the saw lines are laid down wrong will tell you a lot about where to look on a short coupled lineal. So when is a traditional edger the better choice? The short answer is, if you need higher throughput than a short coupled lineal can deliver, or you need wane up down scanning. And another thing I would add is if you need your edger to really police thickness issues, then you're better off with wane up down scanning. And a more traditional machine is going to be a transverse edger in particular is probably a better choice. most edgers don't have to police thickness that much. You're not looking for it to look at a wedged piece and go, oh, I need to edge off, you know, an extra amount on this edge because it's too thin. It's a rare problem, and you can just leave that alone until it gets to the trimmer and you don't have a lot of consequences. If you have room for the kind of throughput that these edgers can give you, and you can turn the pieces wane up, you have a really simple and effective and highly accurate system on your hands. And I'm going to turn it over to Joey now to talk about the scanning. Scanning is the defining feature of these systems. By shortening up the scan zone, it becomes possible to have a short coupled lineal, and then you just have a really fast setworks and fast solutions to marry with that. So take it away, Joey.
All right, thank you. So the reason the scanning is so important is if you really want to cut down the length, on a typical lineal edger, most of the length is taken up by the scanning. Additionally, though, as this shows, on one of these short infeed edgers, you have very, very little time for both scanning and optimization before you need to get the saws moving to where they will enter the piece. So at 500 feet per minute, it's 120 milliseconds for every foot of travel. And so if your optimization takes 120 milliseconds, that means you have to add another foot of belt between the scanning and the edger. So you've kind of seen this one before, and there's a reason. This is really what you want for anything in your mill. You want to increase throughput and you want to improve recovery. And the scanning system really is the heart of this. If you don't have the right scanning system, you can't achieve the throughput or the recovery. You know, scanning and optimization is what makes high throughput, high recovery sawmilling possible, and particularly so on short coupled infeeds. So we've kind of got three things we're looking for in a scanning system. It needs to be reliable. It needs to be reliable for the whole life of the system, which means it also has to have a long support life. It can't, you don't want to buy it and have it go obsolete and have to, you know, do a whole system upgrade shortly after. It needs to be fast, and in this case, it needs to be fast in a very particular way to be able to scan a piece in as little travel as possible. And it needs to be accurate, because the accuracy is what really determines how well the optimizer is going to be able to accurately predict the best solution. So in reliability, you know, you want a hardware that is really designed for sawmills. If you're putting a scanning system into a sawmill, it needs to be rugged and able to handle just the brutal conditions in any sawmill application, where there's sawdust, there's vibration, there is often pretty large temperature swings, and it really needs to have a long support life. When these scanners go obsolete, you're really at the mercy of you know, your scanning system, maybe being able to buy some used parts on eBay. You might have to rob the Smithsonian. It's not a position you want to be in. So you really want to look for a scanner that's going to have a long support life, but the manufacturer is going to stand behind. And you know, companies that are making hardware for sawmills will stand behind their equipment because they know that's a requirement. The speed is, like I said, really critical on these systems, and the particular solution that we use is a multi-zone snapshot style scanner, and it's something that's really unique to sawmills. That there's really not a lot of other places or industries that need this type of scanning technology, and so it's, for us as a sawmill scanning company, this is a really kind of key and interesting product, and one that there really is. You know, you're not going to find a lot of other vendors outside of sawmills that are providing this type of technology. In addition to the the scanning, the multi-zone. The other thing is you really want a scanning system that gets the data to the optimizer as fast as possible. And so our scanners all do real-time processing of the profiles as they're generated and send them to the optimizer in real time, so that by the time the board leaves the scanning zone, it's already in the optimizer and ready to optimize. And this is one of the keys to getting that total time down as much as possible. The other thing, I guess, is these systems require often a lot more integration between the optimization and controls, because you have so little time that if the optimization takes slightly longer, you might need to slow the belt to give the saws more time to adjust, or you might need to slow the belt because the decision required the saws to go all the way from one side to the other, and that takes a little bit longer for the set. And so it's not, oftentimes in a transverse and longer lineal systems, it's kind of a set it and forget it, and you set it for the worst case and it just keeps going. On these ones, oftentimes you benefit a lot from having a lot more collaboration on optimization controls. So the solution to getting the scanning down in a short infeed is to have multiple zones. With a single zone lineal, you need the board to travel its entire length through a scan zone before you have the full scan. By adding additional lasers, each laser only needs to cover a part of the flitch's length. And so in this case, we've got 3 lasers, so the flitch would only need to travel a third of the length to get a full scan. For the short coupled infeeds, we take this one more level, and so we put scanners with multiple lasers, a lot of zones. And with this, with very, very little travel, you can get a complete scan of the flitch. So in the JS25X6B sensor that we use for these, it's just 6 inches of travel. And so you place the board on the belt, a little bit of time to settle, and then 6 inches of travel, and the board is scanned and into the optimizer and ready to be optimized. This is a real key in making these systems possible. It also, simplifies the system to have multiple lasers in one scan housing. There's less components, less cables required. So it's really a nice system for these type of edges. So what do we want in a scanning system? We want a scanner that's really designed for the needs of that system, and so it needs to have the right kind of scan envelope and the right kind of accuracy that's needed for getting a good optimizer decision. It needs to be able to identify the difference between steep wane and sawn edges, because that's one of the really critical things on many edges. You need a lot of data, so you want it to be able to scan fast and have a lot of points across the board, so that you can really see where the wane is as accurately as possible. The solution for lineal edgers is really nice on scanning. It's one of the things that I think makes lineal edgers better just in general than a transverse edger. So the thing you really care about is really where the wane meets the top of the board. And with a transverse edger, you're usually scanning just top and bottom scanners, and so you don't get a great view of the wane, especially on steep wane. It's often problematic for a transverse scanner. With these scanners, you are coming in at really an ideal angle to see the most critical part of each flitch, which is where the wane meets the top of the board, and this really gives the optimizer the best data they could have to make great decisions on each flitch. The other thing you need is in sawmills on these edgers, it's not like a lot of other scanning applications in other industries where everything's really uniform, the lighting's clear, It's just the same thing over and over. With boards, you've got a lot of different characteristics and darkness of the wood, darkness of the bark. It might have been raining, and so the outside of the wood is darker and wet. And so you need a scanner that can really adapt to this type of conditions. And so our scanners use quite a bit of technology to automatically adapt the scanning to get the best data on any given flitch, regardless of its kind of darkness conditions or kind of the way that flitch looks. You want it accurate, and one of the keys to accuracy is being able to calibrate it well. In a calibration system, the key is, it needs to be a good calibration system and get an accurate calibration. But that part's actually fairly easy. The more important thing is that it needs to be easy to do with as few steps and as little complication as possible. Because if it's difficult or complicated, there's a good chance it won't happen as often as it should. There's a good chance that when it does happen, occasionally mistakes will be made. And so we really focused on making our calibration system very, very simple and approachable, so that it's easy and quick to get a good calibration as regularly as you need. There's some really good resources on how to maintain not only the scanning but the entire lineal edger system. So McDonough has put together a great guide. It's really applicable to any lineal edger. It doesn't, it's not really specific to McDonough. It's applicable to whoever does the optimization and scanning. We've got a link there on the slide. Also, if you just want to email us, we could send you that PDF as well. So in the end, again, what we're looking for is a machine that is easy to set up and maintain, reduces downtime, makes sure the best lumber you can get from your raw materials to increase your throughput, improve your recovery. And Peter's going to kind of walk through some of the questions you can ask when you're looking at these systems to help you achieve these goals.
So questions to think about. Is the system easy to set up and maintain? What piece count do I need to hit? How reliable is it, and what's going to break first? Good thing to ask people who own one. What's the slowest part of the system that's going to be the thing that holds you back? How long will the hardware and scanners be supported? And will our crew be able to work on this system and understand it? Is it easy to set up and maintain? What's the least accurate part of the system? How long will it stay at the initial performance? How stable is the infeed belt? Can it distinguish square edges from steep wane well? Can it see dark wane and wet wood well? So back to you, Joey.
All right. So, there's a number of vendors out there that make this kind of machinery, and certainly these are people you could reach out to if this sounds like the type of system that would fit well in your mill and your requirements. Certainly would recommend reaching out to any of these companies. They've all have experience in making these short coupled lineal feeds. And now we'd like to open it up for questions.
All right, thanks, Joey and Peter. I really enjoyed hearing about the benefits of short coupled edgers and the scanning solution you've come up with. We've got a couple of questions from attendees already. First off, what would be the length accuracy plus or minus of the scanning solution, and does it use high-speed photo eyes?
That would depend a little bit on the system. Some of them would use high-speed photo eyes. The raw scanning length accuracy is on the order of, an inch or maybe a little bit less than an inch.
Okay. And I believe you mentioned that some of the short coupled edgers are harder to calibrate than transverse edgers. Why is that?
Transverse edgers, you just lay a calibration object and you scan it more or less exactly the way you would scan a board, the optimizer picks up the information and calibrates itself with that. With a short coupled lineal, it's a static process. You have to lay the calibration object down on the belt, and you have to take great care that it's in exactly the same place that you always put it. So you have to be prepared for that. It's not difficult. And then the calibration is quite simple. You just say go and it calibrates itself.
Okay. And you mentioned that there's less maintenance required when it comes to short coupled edgers. Do you have any figures in terms of the saving costs with that?
Don't have figures, no.
So how do different species of woods impact the accuracy of the short Infeed?
Well, I think Joey should speak to that because it's more about scanning than anything else.
Yeah, I mean, that would really be an issue on scanning. In practice, no.
That's my impression too.
Can adapt to pretty much any species of wood.
So we have another question. With regards to scanning from above, what is the thickness accuracy measurements?
You know, there's the thickness accuracy of the actual scan measurements, which is great these days. And then there's the accuracy of what you know by only seeing the top surface of the piece, and that's why weighing up down scanning can help you. If you have twisted boards or bouncy ends, then you can really see the difference between a weighing up down scan and a weighing up only scan. But in practice, with most wood, most species, it's good as long as I said, you're not really looking for your edger to police thickness on, you know, lots of boards that have flaws in that. If you're mostly looking for it to see where the wane breaks are and figure out how you're matching wane rules, which is a typical edger, then you're fine. Most people, when they set up edgers, they get annoyed at how picky it is because the scanning is so accurate, and they widen their windows on what's acceptable, even with a weighing up, weighing down system, which tells me that wasn't the key factor, right? You're not really looking for the edger to tell you within 10 thousandths whether you're at the right thickness, because you widen that out.
Unfortunately, I think that's all the time that we have for questions today, but if anyone has any additional questions, you can reach out to Peter and Joey by email.